ball back up to the top again, right? And that takes energy. That is our EMF. It's the thing that's lifting the ball back up to the top of the hill so it can roll down again. Now, in a battery, this is done usually with chemical energy. These are chemical reactions that take place. A common battery, like what you might find in a car, is a lead acid battery, or a lead oxide acid battery. Right? You've got a lead terminal and a lead oxide terminal immersed in a solution of sulfuric acid. And the work that's being done there are chemical reactions. Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 108, resistor circuits and batteries. All right, so last time we talked about resistors and how, like for a wire, it will have some resistance associated with it, right? The intrinsic properties of it we called the resistivity, and then when you took into account the diameter, the cross-sectional area, and the length of the wire, you could get a measure of some resistance in ohms for a length of wire. But it's usually very small, and so in electric circuits, we'll always assume that the wires themselves have negligible resistance, and so we'll call that resistance zero, and so we won't even account for it. Instead, we'll have little lumped elements called resistors, which will have anywhere from ohms to kilo ohms to mega ohms, providing lots of resistance for a variety of reasons in electric circuits. And we represent it schematically like this. We'll have an attachment point A, an attachment point B. This is like the input and the output of the resistor. And it'll be characterized by some resistance that's measured in ohms. So what happens in that resistor, right, when you pump electrons into it, right, or current carriers, right? You remember that our microscopic model, right, showed that the electrons were colliding with the ions in the metal that made up the conductor, right? And they're losing energy to it, thereby creating heat. Yeah. And so power consumption, a little bit of work can be done by moving a little bit of charge across a potential. And if I divide this on both sides by dt, then on the left-hand side, work per time, well, that's power, measured in watts, which are joules per second, yeah? And on the right-hand side, I get V times dq dt. Well, what is that? That's the change in charge per unit time. What is that quantity called? Anyone remember? We talked about it in the last lecture.
Did you say that change in...
The change in charge per unit time. So if you see some number of charges going by per second, what do we call that? It's called current. I. So the power is equal to the potential times the current. But there are other expressions that we can, if we're considering ohmic material, that's resistive elements like resistors, right? Then we can use Ohm's law, V equals IR, to substitute in for I, for example, which is V over R. So that would give us V squared over R. But we could have substituted in for V instead, in which case we would have gotten I squared times R. Now don't be confused by the fact that in one case it's inversely proportional to the resistance, and in another case directly proportional to the resistance. These three terms we would use in various circumstances. If we knew what the current was through a resistive body, we would use the rightmost. We'd square the current and multiply it times the resistance, and that would give us the power dissipated. If we knew what the potential across a resistor was, we would use this one here, V squared over R. Yeah. If we had, say, a starter motor, for example, and we knew what its power rating was, we could use that to calculate for a given battery of voltage V what its current needs would be, how much current it's going to draw. And that'll be a problem that you have in one of the homework assignments. But that's power. That's the rate of work that's done, yes? And so what's the work being done here? It's making heat in a resistor. Right? It's just making heat. That's all it's doing. In a starter motor, it's turning a wheel, which is turning the engine, which is getting it started. That's what it's for. But here, for resistors or ohmic materials, the work that's being done is just making heat. During editing, it occurred to me that there is an analogy to this P equals I squared R and P equals V squared over R that may be enlightening. And this analogy comes from classical mechanics. The kinetic energy of a particle can be written as 1/2 mass times velocity squared, in which case the energy is directly proportional to the mass, or it can be written as p squared over 2m. In this case, the energy is inversely proportional to the mass. The equations for power should trouble you no more than the equations from classical mechanics. So, I don't want to get into the details of why we would want to do that. I mean, well, one reason you might want to do that is if you were cold and you wanted to get warmer. That's what a heater is, right? You run electricity through these resistive metal bodies. They heat up, they glow red hot, and you get heat, yeah? Sometimes you can make light. Those are resistive bodies too, though, whether they're ohmic or not, it kind of changes. The resistance changes as the temperature increases, and so it's kind of complicated. But these will be the resistors that we'd put in, say, an electric circuit or an electronic circuit. And I want to talk about how do we add them in combination. All right, so a complex of resistors, how do we account for their total resistance? And it's not as hard as you would think, but let's put two together here. So we'll call this C, and we'll call this R1, we'll call this R2. So the potential, and also I'm going to assume that V sub A is greater than V sub B, which is greater than V sub C. So this is high potential on the left, this is low potential on the right. As we cross each of these resistors, our potential will drop because we've done work. Once we've done work, our potential decreases. Because remember, potential is the potential energy per unit charge. So we can write that the potential VA minus VC, the potential difference across these two resistors, is equal to VA minus VB, that's the potential across this one, plus VB minus VC, that's potential across R2. So we'll write this as V, just call it V, equals VA minus VB, that's the potential drop across resistor 1. Oh, that is what I want to write. I want to write this as VR equivalent, because what I want to do is replace these two resistors with a single resistive element, at least abstractly or schematically, because you do this from time to time. You want to know how putting different resistors in combination with each other, how that'll change the total resistance on the circuit. And we haven't even talked about circuits yet, but you get the idea. So V sub R1 just means the voltage drop across the first resistor, and VB minus VC, well, that's the voltage drop across the second resistor. So the voltage drop across resistor R1 is just I times R1, and the voltage drop across resistor 2 is just I times R2. But I is the same in both, so we can factor that out. If I wanted to replace these two resistors with a single body, I could write this as I times REQ, some equivalent resistance, which is going to be equal to I times R1 plus R2, which just says that the equivalent resistance is just the sum of the individual resistors. And so for series, REQ is equal to R1 plus R2. In series is not the only way I can connect resistors, however. I can also connect them in what we call parallel, and it looks like this. Here's our point A. We branch off into two separate branches, and then we reconnect down here, R1, R2. Now this time, the current is not the same through both, right? We have a junction here, a junction where we split our current into two different paths. They'll recombine here later, but the total current through this thing is going to be equal to the current through the resistor 1 plus the current through resistor 2.
Okay.
So remember in the series, right, the potential across the first resistor and the potential across the second resistor was different because you have a voltage drop after you've gone across the first resistor. Here, the potential across the two resistors is the same. So that's how they are different. But we can write that the current is equal to the sum of the currents through the two arms, and I can just simply replace this with, using Ohm's law, V equals IR. I just solve for I get V over R. So this is V, which is the same for both, over R1 plus V over R2. I can write this as V over R equivalent, where this is the resistor, the value of the resistance that I can replace these two with. And you see that this time what we get is that 1 over REQ is equal to 1 over R1 plus 1 over R2. So it's the inverse of the equivalent resistance is the sum of the inverses of the resistances that make up the parallel circuit.
Yeah.
And so I'll write for parallel, did I spell it right? I don't know. I always misspell parallel, I think. That's it. We have 1 over REQ is equal to 1 over R1 plus 1 over R2. And in your homework, I will ask you to show that this implies that REQ is equal to the product, R1, R2, over the sum, R1 plus R2. And a more useful, well, sorry, that's not a more useful, but this can be handy if you want to calculate the equivalent resistance for a parallel complex of resistors. If you had 3 resistors in parallel, or 3 resistors in series, if you had 3 resistors in series, the equivalent resistance would just be the sum of all 3 resistors, or resistances. That's a tough word to say, resistances. In parallel, it's going to be just like this. So if I had 3 resistors, right, one, all connected in parallel, right, like this, then 1 over Req is just 1 over R1 plus 1 over R2 plus 1 over R3. And so you can see where that's going. If you were to put 4, you would have 4 inverse resistances added together to get the inverse of the equivalent resistance. And I think that's all I wanted to say about that. So we know now how to combine resistors in series, combine them in parallel. And so let's talk about voltage dividers next. So I want to talk about voltage dividers next because I want to talk about batteries. But before I can really talk about that, I got to talk about circuits. And so what is a circuit? Anyone have a guess as to what a circuit might mean? Has anyone ever heard of like circuit training, like a gym?
Yes.
Yeah, where you go around. Yeah, it all has to do. I think circuit. The CIR part probably comes from circum, from Latin, which means around. So a circuit is a loop essentially. And though I'm going to introduce batteries before I introduce batteries, so just bear with me. But imagine the following. This I'll call just an ideal battery. It's a thing, it's a device, which we'll talk more about in a minute, which creates a potential difference between these 2 points here. We're going to connect these up, by the way. We'll have R1 here, and I'll put R2 over here. And then I'll just connect these together. So that's the circuit, right? We always start from high potential and go to low potential. Let me just remind you again about current, right? The current I, if it's going in this direction, that means that positive charges will be traveling in this direction, same direction as the current, but negative charges are traveling in the opposite direction. It doesn't matter which is which, the current is still going that way. So this is going to be a battery eventually. Okay, we'll talk about that in a minute. And so this is the negative terminal of the battery, and this is the positive terminal of the battery. And so in reality, in most batteries, all batteries I know of anyways, there will be electrons provided at this negative terminal, and they will be flowing around the circuit like this, counterclockwise, as I've drawn. But the current is always going the opposite direction. It's going from the positive terminal to the negative terminal, by definition. It's unfortunate that that's the way it is, but it is. If it was some weird battery that happened to provide, I don't know, positrons, right, which are they're positively charged electrons, antimatter, it would explode here on Earth anyways, but a positron battery, right, these positively charged electrons would travel in the same direction that the current is indicated here. So it's a point of confusion that baffles people. One of the common mistakes they make is they think that, well, since it's electrons that's carrying the charge, then the current is going to go this way, clockwise or counterclockwise. No, the current will go clockwise while the electrons will be moving counterclockwise in the circuit. So always think of, and I always just think of positive charge carriers, okay? Even though I know almost all charge carriers in circuits are electrons, okay, and are negatively charged, and they will just be going backwards from what I'm thinking of. You understand?
Yeah.
Okay. Here we have 2 resistors. Are they in series or in parallel? Series or parallel?
Parallel.
Yes, parallel. So, no, they're in series. Yeah, I know they look like they're in parallel, but they're not, okay? You tricked me. You were so convinced of your answer, you tricked me. They look like they're in parallel because you see 2 parallel lines, right? They're actually in series. The output of this resistor, right? Remember, the current is always going from the positive potential to the negative potential, right? From high potential to low potential. So it's going clockwise, right? So here our current is going clockwise in the direction that the clock turns, right?
Yeah.
Which means this is the input, this is the output, and the output of this resistor is at the input of this resistor, you see?
Yes.
This would be the same picture if I were to stretch this wire. I could have drawn it like this. Here's my battery, R1, R2, yeah? It's the same circuit. Because remember, these lines, right, I mean, they're not real, they just represent where the connections are made, okay? I put this resistor down here at the bottom just to have convenience, right, for drawing. So the potential along this wire, whatever it is here, it stays at that potential until it arrives here, at which point it drops again because we have another resistor, right? We're always assuming the wires have 0 resistance, so they're not going to drop the voltage at all. I guess I can leave that up. These are the same pictures. But what I want to talk about is if I were to measure the potential at these 2 points here, A and B. Oh, that would be the same, of course. That's not what I wanted to draw. Sorry. Let's make this A, B, we'll do it like this, C and D. If I were to measure the potential drop across here, or across here, I want to know what I would get. So you may recall that because the electric potential is a conservative force, that if I move some charge from some point, say here at this high potential, and I go in a circle, well, let's just think of it differently. Think back to the days when we talked about charges distributed out in space, right? So let's say I have a positive charge over here, and I have another positive charge, and I bring it in, and then I take it right back to where I came from, right? Have I changed the potential at all? Have I done any work? That's what I'm trying to say. I have not, right? Because if I take the charge from here and I move it closer, I have to do work because these two positive charges are repelling each other, yes?
Yes.
But then, to get back to the point that I started at, the electric field is going to do the work for me, you see? So it's paying me back. So I have positive work I had to do here, and then negative work is done for me by the electric field. So the total work that I've done at the end of the day, if we keep accounting like that, right, is I've done no work because I first had did some positive work, and then some negative work was done. They completely erased the positive work that I had. And so this expression here, which is it's a line integral, says that the electric field around some loop that comes back to where it starts, that's what the little circle means, right? This is always equal to 0. Now we'll see later when we start talking about magnetism that this can be non-zero under certain circumstances, but we'll get to that. But for static fields, right, or electrostatics, this is true. And that means that if I go around this circuit, starting at the positive terminal and then returning to the positive terminal, there will be no work done, which means that I can add this up. I can say, well, let's start at the negative terminal. When we go from this spot here where the minus sign is to this spot here where the plus sign is, that means we've increased our potential, right? How much? Well, I'm going to call it VB for V of battery. So that's a positive increase in potential. And then we move around the circuit. No potential drops through the wire because we're assuming the wires have no resistance. And then we go across this first resistor, R1. Well, that's going to give us a voltage drop. So this time we're going to decrease, so minus. And what is it equal to? Well, we'll use Ohm's law to write that. It's going to be I times R1. And then we keep going around the circuit here. Since we're in these non-resistive wires, we're not really dropping potential at all until we arrive at the second resistor, R2, in which case we'll drop yet again. Minus I R2. And this says that this is equal to 0. Now I'm going to solve for I. That tells me that the current through this, right, is just equal to V sub B divided by R1 plus R2. Which means that I can rewrite, I'm going to erase this circuit down here, the voltage drop across R1, which of course is equal to the current times the resistance, right? And the current is V sub B over R1 plus R2 times R sub 1, right? This is I from here, and this is R, V equals IR, right? But we can rewrite this as R1 over R1 plus R2 times V sub B for V of battery. And then what about the voltage drop across R2? Well, VR2 is equal to the current VB over R1 plus R2 times R2, which we can rewrite as R2 divided by R1 plus R2 times V sub B. What if R1 and R2 were equal in resistance? So let's let this be 1 ohm and this is also 1 ohm. Or maybe we make this, yeah, that's fine. 1 ohm and 1 ohm, right?
Yeah.
Running out of room here. We'll write it up here. So let's let R1 equal R2 equals 1 ohm. Then what is the voltage drop across the first resistor? V sub R1 is going to be equal to, well, R1 divided by R1 plus R2, right? That's going to be 1 ohm divided by 1 ohm plus 1 ohm times V sub B. Yes?
Yeah.
That's equal to 1/2 V sub B. So we've halved the voltage, you see? That's why it's called a voltage divider, right? So I could get that half voltage by either connecting to points A and B or connecting to points C and D. I think in the homework I'll ask you to create a voltage divider that gives you two possible outputs, you know, a third of the battery's voltage or 2/3 of the battery's voltage. And you'll do it in a very similar way that I did this here. That's what it's used for though. Imagine you've got some component that, you've got a 3-volt power supply and you have a component that requires a potential of 1.5 volts. Well, voltage divider, right? Get two equal resistances, connect them up in series, right, with the battery, and just connect across one of the resistors, and there's your 1.5 volts. The reason that I mentioned voltage dividers first is because, before I talked about batteries, is because we can think of a battery, a real battery, not an ideal battery, as a voltage divider. Now, any idea why an ideal battery cannot be thought of as a real thing, right? Why can't you have these ideal batteries where the potential always maintains, you know, 12 volts or 6 volts or whatever it is? Well, I'll let you think about that. And that's a problem worth thinking about in your head and asking what's wrong with that? Why couldn't such a battery exist that never drops in voltage when you connect across it? But okay, let's talk about batteries next. When I talked about voltage dividers, I had mentioned that for a conservative force, right, E dot dl, the closed path integral of E dot dl is equal to 0. So if I write F as the force per charge, and let this be equal to E plus some source, F source, right? Then I can rewrite this path integral as F dot dl. The E part will be 0, and all we'll be left with is F source dot dl. And this electromotive force, EMF, it's not really a force, except that in this integral, right, it's a force per unit charge. EMF is a voltage, okay? It's measured in volts. EMF is what determines how much current will flow through a circuit. So let me just make an analogy to a circuit in the form of, so imagine a table with these pins, and we have a ball which is going to roll down the hill, bouncing into these pins such that it travels through at a constant velocity, the drift velocity. So the ball is analogous to our electrons. It's rolling down the hill because it is elevated above the ground some distance h, right? And gravitational potential is g, the acceleration due to gravity, mgh. That's the potential energy. Once the ball gets to the bottom of the hill, however, how do we get it back up here to the top again? Somebody has to lift this up. So we need some kind of ball jack that can lift the ball back up to the top again, right? And that takes energy. That is our EMF. It's the thing that's lifting the ball back up to the top of the hill so it can roll down again. Now, in a battery, this is done usually with chemical energy. These are chemical reactions that take place. A common battery, like what you might find in a car, is a lead acid battery, or a lead oxide acid battery. Right? You've got a lead terminal and a lead oxide terminal immersed in a solution of sulfuric acid. And the work that's being done there are chemical reactions. I'm not going to go, I thought about going into the details of the chemical reactions, but to really do it justice, we'd have to go into the chemical kinetics of it, and that would be complicated and take a lot of time. So we'll not do that, I think. In our voltage divider example, we talked about ideal batteries, batteries whose maintain a constant potential difference across the terminals. Let's see if I can draw some semblance of a battery here. So the positive terminal and the negative terminal correspond to the plus and the minus that I put here in the circuit diagram for a battery. Notice that I put more than one of them, right? Battery is called a battery because it's a series of cells. So for most chemical cells, you can get anywhere between a volt and maybe 2 volts potential difference. And so by putting them together in series, you can increase that to, you know, make a 6 volt or a 9 volt or a 12 volt battery. 18 volt is another common one. I think those are boat batteries. And so usually when they draw these, they draw, you know, 2 or more cells together to represent a battery, because that's what battery means. It's like an array of stuff, okay? Array of cells. And so I'm going to represent the battery like this. And then I'll put here, I'm going to call this big R, and I'll just write load underneath it. And then I'll write little r here, and I'm going to put a box around this. This is the battery. This little piece of the diagram that I've drawn here, this source of voltage, right, V sub B, and this little resistance R, called the internal resistance of the battery, that represents the actual battery. And then our load is whatever we connect up to the battery. It could be a starter motor, it could be, the radio in the car, if it's a car battery, right? Whatever you're going to connect the battery up to, that's the load that you're putting on it. And so this internal resistance, what does it represent? It represents stuff that's taking place inside the battery. If it had a very high resistance, it would be because the chemical reactions that are taking place to create the EMF are slow. If they're very fast reacting, then you would have a lower resistance, internal resistance. Okay, there's also heating that's going on in the battery. There are ions in the electrolyte that are being transferred from cathode to anode. But if you look at this, you can see that this looks like a voltage divider, yes? And we can think of it as a voltage divider in terms of our load and this little resistor R. Remember that the current travels around in a loop, right? And the funny thing about batteries is that as we're traveling through the loop, we're going from positive, the current is going from high potential to low potential, from the positive to the negative. So it's going around this loop, making its way to a lower potential. But once it's inside the battery, it's going from low potential back to high potential. Okay, that's where the chemical energy comes in. The chemical energy is doing the work to go from low potential to high potential, because to move a positive charge in a field from low potential to high potential, you have to do work. That's where the chemical energy is coming into the battery. So the potential difference across the terminals of the battery, which I'll just write as V sub B, remember that's really a delta V, right? It's the difference in potential between the positive and the negative terminal. And that can be written as, well, if we work our way around the loop, and let's ignore the load for a minute, let's just like short circuit this battery like this, cut that out, yeah? If I short circuit this thing, I've got a little circuit like this, just flowing around, yes? This would be like if you took a screwdriver and laid it across the terminals of the battery. As we move around here, we go through the seed of EMF, and we get this increase in the potential because of the EMF, but then we drop some because of the current through the little resistor R. If we then attach the load to the battery, once we put the load in, I is going to be equal to delta V over R. The load our load, I guess I'll put it. This will be E minus IR over R load. Since IR plus I little r is equal to the EMF, then I can solve for the current. It's the EMF divided by the sum of the resistances. And so the terminal resistance across the load, we can think of like a voltage divider with R load over R load plus little r times the EMF of the battery. So that's what I meant by batteries. Real batteries are like voltage dividers, right? In that they're the terminal, the potential across the terminals, right, is like a voltage divider with the EMF. And I put some problems in the homework that deal with batteries and looking at the voltage drop in certain conditions and stuff like that should be instrumental in trying to, firm up your understanding of that. And so with that, I think that's all we're going to cover in this lecture. Next time we'll talk about RC circuits, that's resistors and capacitors in combination. We have in a previous lecture, I forget which one, the one about capacitance, I think, talked about capacitors in series and capacitors in parallel. So you'll need to review that. It's very similar to resistors. It's just kind of reversed, right? So capacitance in series is like resistors in parallel and vice versa. And so we'll talk about RC circuits and also Kirchhoff's rules for analyzing circuits. And that's what we'll do next time.